guys, welcome to the 7th session of number systems for MBA aspirants or for any aptitude exam or college placement exams that you are going to be giving. So as I have been saying since the first session that rather than the direct questions in majority of the exams, you will find that this topic is going to be the core or rather than the foundation where several questions are framed by combining them with other topics. In any case, this topic is going to be very useful because almost majority of all of them will have applications of this. So till last lecture we had seen how to find the total number of factors for any given number, right? Now let's take it up a notch and this time let's see what if we are required to find the sum of all factors. It may be for any other computation or operation that we need, but for some instance we need the sum of all the factors for any given number that we have to do the further operation or further calculation. So how do we go about it? Now I am sure you guys must have left the space that I had instructed, so I will be taking that same example of 528. We have done this much prime factorization till last time, and we know that 528 equal to 2 raised to 4 into 3 raised to 1 into 11 raised to 1. Now the only difference between sum of factors and total number of factors is how we go about using the permutation combination values that we are getting it. We will be using the same data, because as we know, this prime factorization that we have written here, what does it show? It shows that 2 has 5 possible values, 3 has 2 possible values, and 11 also has 2 possible values for making up this number in several other pairs, right? So for summing all of them, what I'm going to do, I'm going to add them. This is how it's happened. I know that there are 5 possibilities for 2, right? One is 2 raised to 0, 2 raised to 1, 2 raised to 2, 2 raised to 3, and 2 raised to 4. That is the maximum. So I will add all of them and multiply it with the similar cases of 3 and 11. And this in the end will give you the final value that we are requiring. Quite simple, right? We have done nothing but just use the permutation and combination to solve our complex problem, which was not so complex at all, right? So I'm sure you guys will find it quite easy and you must have gotten the gist of how to go about it. Just add all the possible values for the prime factor from 0 index to greatest index which is present in the factorization and multiply it with the other possible values of prime factors, and at the end you will be left with the sum of factors. Quite easy, right? And in our case for 528, 1488 is the sum of factors, and I would encourage you guys to better check it out. I may have intentionally left it wrong for you guys to point it out, and I can also know whether you guys have actually done it or not, right? Anyways, now since we have gotten that concept, let's try a few questions. But before that, I would like to show you a tricky question. This is the one. How many 2-digit numbers have exactly 3 factors? This is the theta type of question. So yeah, it would be best if you guys can solve it by yourself. Pause the video and go ahead, and while you are doing that, I will continue my work. So as we all know, 2-digit numbers include all the numbers from 10 to 99. Now the exactly 3 factors condition, if you have watched carefully till now all our sessions, I have previously told you that only a unique set of values satisfy this condition of having exactly 3 factors, and those are the square of prime numbers. Because square of prime numbers, they will always only have one factor greater than the prime numbers themselves, that is themselves. Anyways, let's take an example. What is the prime number that comes to your mind? Let's say 2. Square it, you will get 4. Now for 4, what are the factors? 1 and 4 itself, obviously, and the only possible value by which we can get 4 is by multiplying 2 with itself. So 2 is the only possible value that remains apart from the number and itself. So there is the condition that you are getting only 3 factors, and it is true for every prime number. So let's try a sequence of multiplying prime numbers by themselves. So we have 1, 4, 9, 29, 49 and 121. We already gotten to our 3-digit number, so we don't even need to look about it. We are only interested in 2-digit numbers, right? So the square of 5 and 7 are satisfying our condition. And mind well, I have not taken any composite number square. I have only taken prime number square for our case. That's why 1 is also not here, because 1 is neither prime nor composite. So These are our answers, 25 and 49. So there are only two such two-digit numbers who are having exactly three factors. So quite interesting, right? This is quite a, a question where your remembrance power or property understanding power is checked. And this type of question come in snap and cmat like exams where you only have 1 minute to solve a full question completely. Well, let's move on to our today's main topics, practice sets. That is sum of factors of 192. So we will first need to factorize it, and obviously if you know divisibility rules, you can directly find it, because 192 is clearly 9 plus 2 plus 1 3, so it is divisible by 3. So 3 is only having one factor, then you will get 2 into 6, 2 raised to 6. And for sum of factors, now I already know 3 raised to 0 plus 3 raised to 1, that is 1 plus 3, multiplied with 2 raised to 0 plus all the way, I will keep adding till I get 2 raised to 6. And then I will finally get my answer. Now, adding here, you also must have noticed there is quite a smart trick to it. For instance, if I add 64 plus 16, I will directly get 80. That will be easy to add and multiply. Then again 8 plus 2, they will give me 10. I already got 90. So 95 will be my final for this whole bracket, and 95 into 4 I can solve it. And even that 4 into 95, you can do it in a roundabout way. Just multiply with 100. 400 minus 20. That is much simpler. And you don't need to write such things, because multiplication of 100 and multiplication of pi are very easy. You can do it in your mind itself. So just for demonstrating you how I go about it, I have written all this, but you don't need to write. So in essence, when you need to find sum of factors for such a number, your answer will be coming in the third step itself. You won't be required to do all this calculation. Just after writing this bracket 1 plus 3, 1 plus 2 plus 4, after that the next step you will directly get your answer if you know such small tricks, right? Let's move on. Now, again, a roundabout way of stating a simple question. Find the sum of factors of O if O is the sum of factors of 135. Now, first, it might be quite complicated for many of you guys who might not be from English medium or something, but let's keep it simple. First, I need to find the sum of factors of 135. That is the essence first. So 135, again, I can simply write by seeing the pi. I already know pi is the going to be factor. So divide it by pi and you will be left with 27. So sum of factors of 135 is O, right? So what is my value of O then? Well, O is equal to 1 plus 5, 1 plus 3 plus 9 plus 27. I'll be left with 6 into 40. Again, here also I don't need to say 9 plus 1, 10, and 27 plus 3, 30. 30 plus 10, 40. Directly you can. Now, our requirement, I must say, was finding the sum of factors of O, not directly sum of factors of 135. So first I found the sum of factors of 135. Now I need to find sum of factors of this value. So I won't be completely adding it here itself. I will keep it in multiplication form and I will do my calculation from here onwards, because I am not interested in what is the value of O. I am interested in what is the SOF for O. SOF is nothing but sum of factors, just a short form. So 6 into 40, I can directly split it, because 6 is equal to 3 into 2 and 40 is 8 into 5. So 8 2 cube and 1 2 I got from 6. So 2 raised to 4. Now again I will do sum of factors for this way. So same thing, and finally you will be left with 744. So yeah, that was about it. The only thing here was you don't need to find the value of O. That is one time saving core thing that you must remember here. Our intent is not O, but SOF of O, which is SOF of 135. So that's why I didn't find the final value. That was the main learning from this. That's why I demonstrated this specific question to you guys. Now let's move to the next question. Now, I am having a number M, which is directly given in the prime factorization form. My headache is gone already. I can already, start thinking my calculations from next point onwards. I don't need to worry about prime factorization. Now, what I am interested in this time, number of factors that are multiple of 6. Then next, number of factors that are multiple of 6 but not 18. Now that's where the tricky part comes, right? It will be very interesting. I'm sure you guys would love it. And if so far you guys are enjoying our lecture, a like to the video would be appreciated, and do make sure to share it with your friends and subscribe to our channel. Now we all know that 6 is 2 into 3, multiplication of two prime numbers, and M is given in the form of 3 into 2 into 5. Of course, that's why we are going to find the factors which are multiple of 6. So what I'm going to do, I'm going to separate this 6 from this whole. By doing that, I'll be reducing the power of 3 and 2 by 1 units. So total number of factors in this case would be 12, 6 into 9. So the only thing that I needed to do was simple. I separated the 6, or rather the prime factors which are responsible for creating the 6, from the whole equation. I separated them, and then for the leftover index I simply did the normal thing, TNF, and I wrote 16 because this is in the form of multiples of 6. So because obviously whatever I find, all of the combinations will have to be multiplied with 6 to make this whole number. So all of them will be going to be multiples of 6 anyway. Now, so what are the combinations that I'm left with? 11 plus 1, 5 plus 1, and 8 plus 1. So I'm left with 648, which will show me that in this whole m value, there are exactly 648 factors which are multiple of 6. Correct? Now, similarly, this time around, I need to find the multiples of 6 in the factors, but they should not be factors of 18 also. Well, again, we will do the same thing. 18 is basically nothing but 2 into 3 square, right? Because it is 6 into 3. So this time around, I will do the same thing. I will separate 18, or the rather factors of 18 from it. So again, the only thing that is changing is the power. So I will be left with 11 into 6 into 9. So 594 is my total number of factors for 18. But mind well, we have to find the factors that are multiple of 6 but not 18. But we already have 6. So what? Now it is the simplest thing. I will simply subtract them. Total number of factors which are 6 but not 18. 6, 18 straight. That's how I write it to simplify it for understanding. So I will simply subtract the factors of 18. Factors that are multiple of 18 and factors that are multiple of 6. I will subtract the total value and I will be left with 54. So in essence, there are 648 factors of the m which are multiples of 6, and 54 of these factors are multiple of 6 but not multiple of 18. So quite interesting, right? Now let's move on to the next part. Now for the last question of the day, before we jump into it, I will like to show you a few special numbers which are very often used in exams to waste your time. They are rather time bombs. When you try to solve questions involving these numbers, they will directly consume a lot of your time if you don't know about them beforehand. And here are these numbers: 997, 1001, and all of this. The unique thing about them is all of them have something to do with prime numbers, or rather they are multiplications of unique prime numbers, which are very rare to come around, and you won't directly find their value that easily. So 997 is the largest 3-digit prime. So if you ever given an MCQ where you need to find the largest prime out of the given numbers, and if you see 997 is the 3-digit number and all other are 3-digit number, then you don't need to check whether the other numbers are having factor or not. You can directly go for 997, because apart from that, all the 3-digit numbers which are greater than it are having factors. In short, they are composite. Similar to that, 1001, it is already, we have seen how it is used to frame several questions. We even got that game time thanks to it, and it is not a prime. First thing first, it is not a prime. Similar to that, 1003, 1007, they are also not prime because they are multiplication of a unique pair. 17 into 59, 19 into 53. For even I struggled when I had to confirm whether they are a prime or not. So I did the usual thing. I found square root of them and I tried dividing it one by one with the primes, and at the end I stopped at 17 and 19. So that's how I got about them. But for making it simpler now, you need to remember the divisibility rule for 17 and 19 and 13 also, because I am sure in many of the books they don't actually give. They give for 2, 3, 5 up to 11 they give. But in many maths book, if you are using non-standard one, or even your school syllabus is different, there might be this divisibility rule of 13, 17 and 19 might be missing. So if you know them, it gives you a good hand in mathematical calculations. Similar to that, 1009. Now that's an important number because it is the smallest 4-digit prime number. It is not divisible by any number apart from itself. And as for 9973, it is the largest 4-digit prime number. So yeah, Again, there might be MCQs where you might be given options. I will even demonstrate this exact thing to you, how it is framed. I even have one question from, I think it was from CMAT or GMAT or such similar exam. And as for 1,01,000, sorry, 10,001, I saw extra zero there, sorry, 10,001, it is also a composite number of 73 and 137. And don't worry, if you don't know the divisibility rules of such numbers, I will show you in the later part of this session how to frame divisibility rules for prime numbers and how you can find the divisibility rule of composite number based on prime numbers divisibility rule. That also we are going to do, so don't need to worry about it. Just remember that these are some unique numbers around which questions are framed to consume your time in examinations. So make sure you remember such numbers and keep a space after this if you ever find more such useful numbers for your future reference. Right now, let's do the promised part. I'm going to demonstrate to you how a question is framed. Find the largest prime from the following: 997, 991, 9987, and 9973. Now, obviously, what we try to do, we try to find, if we are asked largest now, I will try from the largest number, obviously. But if you have remembered that 9973 is our largest 4-digit prime number, you don't need to even worry about it. You can directly take it and go. Now, just for your reference, 9997 is a factor of 13. 9991 is quite a tricky one. It is 497 into 103. 9987 you can directly verify, it is a multiple of 3 by digit sum rule. And 9973 we have already learned, it is the largest 4-digit prime number. So the only part where I struggled in this question was 991, because 97 into 103 is a very tough combination unless you know how to find the composite rule of our other number rules. So that is very difficult because 97 and 103 are very close to hundreds range. So it was difficult, but yeah. And as I know 13's divisibility rule 9997, I could easily verify that yeah, it is not 1. So yeah, in such cases you can directly take 99973 and go ahead with your work. So I hope you guys enjoyed the session. See you again in the next lecture. Thank you.